I just came from it.
Oh, right. No, yeah, he said the same thing in mine too.
I saw all on that one.
Yeah, I told the higher ups, you know, we tried to you should get that full semester.
Yeah, I just checked. No. Yeah, no. Like, what part is it brings to introduce the project early?
Okay, welcome back, everyone. One person online today. Can you hear me?
Well, it wasn't just introducing.
Loud and clear, sir.
Okay.
Okay, that maybe, but at least introduce the project. Just don't hold it off until like the last month.
All right, so let's take today's in-person paper.
You're right. No, he did give us a paper. But we
Actually, we got a question. All right, so what can you do? Can you hear me?
That's when he's like, yeah, I couldn't do it. It's like, yeah, but a week and a half ago, I didn't even know I had.
Can you hear me?
I think the biggest part we get done is second manager.
All right, please have a seat. Let's just take today's attendance. Yeah.
No, it's
Yeah, thank you.
Yeah.
we don't have to do this.
We finished this last class.
No, we have a tiny bit of C2 left before we start D1.
We were going to start D1 today.
Yeah, no, a tiny bit that's left of
Which I
C2.
didn't print because I didn't have time.
Well, the tiny bit left of C2, we will finish.
Because then we're starting D2, I think I think we're starting D2.
No, we're doing C2, so
Alright,
we have the last
so-
one to finish up, but that one takes us to full class.
So there's no new update. So you're basically working on, actually,
Self-taught.
you submitted something today.
And then we're doing D1.
Ah, okay. So today's a Friday. So did you submit project 2B? Did you make up your team for project 3?
So
I'm not gonna check it. Okay, so please make up your own team and start working on project 3. If you don't do it, okay, please do it. It's open. You can sign up freely using Canvas, right? Okay, so please do it. I'm not going to even check it. I don't want to waste time. Go ahead.
I have a question about project 3B.
3B, okay. Go ahead.
So looking at the report, it says that what it looks like is that we're going to need to make, each team member needs to make their own wing and then we grade it.
I guess so, yeah.
ourselves.
Yeah, because I want each person use the software, do some design components, and then present some unique ideas to begin with, and as a team, you choose the best one.
Okay.
That is the point.
So,
In other words, I know what's going to happen. One person do everything, everybody else watches it. It's not the project.
okay. But there's only 3 slots. It only goes members 1, 2, and 3. It
Yeah.
has to go to member 4.
You have 4 members?
We have 4 members.
Just add the 2-4.
Okay.
Or maybe one person give a slack, I don't know, but because this is like at 80 points, I really don't want to change the form because it's going to change the points. So you have 4 members, right?
We have 4 members. Yeah.
Okay, so please distribute nicely. In other words, member 1, 2, 3, okay, design each unique things. I'm the guy choosing the best. Or maybe analyze each person overlooking at one. You can do something.
I am above all.
Okay.
The fourth person is the board of trustees.
Yeah, okay, so it's up to your decision. So it's maximum 4 members, right? Okay.
Yeah.
Yeah. So make sure, okay, so here's the bottom line. I don't want to see one person does everything and everybody else just to watch. That is huge waste of your time, experience. You're not going to run software just like that. So each person, please try to design something.
Okay.
Okay.
Yeah.
And then choose the best.
So I guess maybe what we do is just like have 2 people do one.
Possibly, yes, it's your decision, yeah. So if so, you just put the 2 names on.
All right.
Yeah.
Yeah. We'll figure that.
Okay. Any other question? By the way, wait a minute, Michael is in your team?
Yeah.
He's actually working on special project team also.
Oh, no, I'm not, I'm sorry. That one day.
Yeah,
I
but
just
you're
thought you
kind of
were
working,
referring to Eagle Knowledge.
you're already kind of working in a,
No, I'm with them, yeah.
in a Aero West anyway, you are Aero West.
Yeah, when you asked, I thought
So
you
that
were
means
the
he's-
Eagle Nautics,
you know.
but no, I'm not on that project. But, yeah.
So he's kind of guy probably overlooking 3 people because he knows already, because he's been doing Aero West design, right? using X-Pi 5.
I've been doing economics.
Yeah, this is. Yeah, here we go. So he's the guy overlooking other people. Any other question? Yeah, so, okay, so he's a team lead. Okay.
Yeah.
Any other question? So this is open-ended, obviously. So again, here's the important thing. If you choose to do a minimum amount of work, fine. You just basically don't run stuff. That's the reward you get. If you're really interested in, if you're serious about thinking about, I'm going to be a designing airplane aerodynamically speaking, senior design, do something. This is quite important tool. And then Fu actually recommended me to develop this course with this software, Bowling, senior vice president, head of HR. So those people actually want to recruit you if you have certain level of skill sets. It's going to be a huge sales point. Yeah. So again, it's up to you. Engineering is all up to you. Your team can choose to do absolute minimum work. That's fine. To pass this class, if you think there's a meaning for it, you can go for it. All right. Let me stop preaching. This is not teaching. I hate preaching. I ended up doing preaching all the time. Somebody please stop me. Okay. So you probably don't want to hear those things, but I guess that's the fact. And people don't hire you because you graduate in the middle, because you know stuff and you can do stuff. That's why. And the whole purpose of taking this class is you get that, right? So please take this opportunity. This is open-ended, so you can explore what you can do using this software. This software basically goes all the basics what we covered in aerodynamics in this class. This class is designed based on this software. Okay, so all the core concepts of aerodynamics is covered, and then it's going to be used as is in this software. So please discover that. Discover that means take a look at the software manual and say, oh, wait a minute, this is pantograph, isn't it? Yeah, we covered it. Oh, wait a minute, this is panel method, yes. Oh, this is critical condition, yeah. So those are the kind of things you have to discover, okay? Not using software as a black box. Anybody can do it. So, okay, so that's a huge difference, okay? I hope you make a difference out of this class. Any other question? So please do your best. I know time is running out. I hate that, but please do your best. This is supposed to conclude everything you learned in this class. Okay. If your team is motivated, okay, aim high. Okay. Any other question? Let's move on. Today we are going to finish up obviously Unit C2, and then we get into Unit D1. Okay. So Unit C2, supersonic speed. Supersonic actually go across the border. So people think about this. This is a different regime of flight. Okay. Am I sharing this? Oh, yeah. Okay. So two people online. Can you hear me? Are you seeing my display? Hello?
Yep, you're all good.
Okay. Julian?
Yep.
Okay, good. All right. So let's take a look at high speed, which is supersonic. Your airplane is flying supersonically. Okay. So what is causing a huge difference is, of course, you're going to create shock wave. Shock wave is created because your airspeed, actually flight Mach number is more than 1. At the very nose of your entire airplane is going to actually create a fast shock wave. Okay. It could be attached, it could be detached, depending on the shape. You are going to run those things in L2. Shock wave formation depends on your Mach number and also your shape. Now, the mechanism is actually not quite well known, surprisingly. This is not theoretical. If you run shock wave formation and all that, it's not theoretical. Everything is based on experiments. Okay. So there are certain things fairly well known, which is a sharp edge. If you create the sharp edge, you can sort of predict the formation shock wave. Once you introduce curved surface, now everything is, well, wait a minute. I have to test it to find out kind of situation. Okay. So again, you're going to also run this when you take, if you take flight mechanics, okay, you're going to carefully design the shape of the nose cone, because nose cone is going to determine how much shockwave you're going to create. So your entire airplane in high speed, supersonic speed, entire airplane needs to be inside of the shockwaves created microcone. So that's why this is the only wing you can have. Okay. Because it must be inside of the angle. So that's called mechanical. Okay. So we're not going to talk anything about that here because we are going to just introduce you just the supersonic speed. So supersonic speed comes with additional drag. This is completely additional, something called wave drag. This doesn't show up unless you fly supersonically. That means your airplane is already flying supersonic speed. Your airplane creates a shock wave, and then entire airplane is placed behind that shock wave. Shock wave's job is, okay, supersonic speed decelerated to subsonic speed by going across that shock wave, typically. So this is a deceleration process of supersonic speed, subsonic speed. Now, you have to have a trade-off. The trade-off is obviously the increase of pressure, increase of temperature, increase of density, everything increase. Especially, mass never change. Right? Did you say mass?
Nothing.
Okay, sorry. Oh, that's a violation of conservation mass. What are you talking about? Anyways, so density. This actually changes quite a bit. That's why this is called compression process. You compress air. So this is instantaneous compression process across this thin line called shock wave. So everything changes, especially density of air changes. So you are flying now not in ambient air. Atmospheric condition, you know, okay? Pressure, temperature, density, atmospheric condition of your flight altitude, but no longer that's not the condition. You are flying behind the shock wave, which is higher pressure, higher temperature, higher density. So that is going to contribute to the drag formation. This is called wave drag. So because you have a higher pressure, higher than atmospheric, this pressure is always applying on the surface. This is going to add more drag. This is called wave drag. Okay. So wave drag, again, cannot be theoretically computed. So this is essentially experimental curve fit based equation. This is, again, Prandtl-Glauert equation. Prandtl-Glauert equation, but I actually purposely not using this name because I don't want you to confuse against the other one, Prandtl-Glauert correction for CP. This is actually Prandtl-Glauert equation for lift coefficient, drag coefficient for supersonic flight. And then you notice that the CL and CDW, either both lowercase or uppercase. So this lowercase applies for 2D airfoil, uppercase applies for actually 3D wing of airfoil, 3D wing. Okay. So coefficient-wise, drag coefficient or lift coefficient is about the same if you fly supersonically. This actually indicates that supersonic flight, most important thing, the contributor of the drag is how much frontal area do you have, kind of thing. Okay. So if you want to minimize the drag in high speed, of course, you want to minimize the frontal exposure. You don't want to have a very thick cross section of huge fuselage. It's always negatively contribute to the wave drag formation. So that actually also constrains your design in high speed flight. Okay. So it's just an introduction. More details will follow in Aero 2 since you are Aero track. So let's take a look at the last page of this unit C2. Example, this is just the estimated drag coefficient of this Mach 3 flight. This is X43 hyper X. So let's consider a thin supersonic airfoil. Thin supersonic usually indicates probably flat plate with little bit of camber. That's typically called thin supersonic airfoil, okay? Chord length 10 feet, oh, very big. This is in a Mach 3 free stream, altitude 22,000 feet. Go ahead, question.
Did you say that the little CD is only 2D and then big
AC is for the.
Yes, I said that.
I think it should be right in there.
Huh?
Never mind, thanks.
Okay. All right, I said that. Okay, altitude 22,000 feet. The airfoil is at an angle of attack of 5 degrees. Calculate the lift and wave drag coefficients and the lift and wave drag per unit span. So we are going to start with angle of attack 5 degrees given. Okay, so I'm going to convert it to radian, multiply by pi divided by 180. This is going to be 0.087266 radians. Okay. The important thing is the equation given here. Alpha is in radians. Be careful. Okay. There are a few equations that specifically you need to be radian. So in that case, if the degree is given, you have to convert it to radian. Let's be careful about this. So that's why I'm converting here. So let's just to pick it up. CL for high speed. This is 4 times alpha divided by square root of Mach number square minus 1. Let's just grab it. 4 times alpha, which is in radian, 0.087266 radian, divided by square root Mach number, this is a 3, right? If you plug in, CL is 0.1234. How about, yeah, question?
Yeah, I just wanted to be technical about the CL. So I know it's the same as supersonic speeds, but would you write big CL or little CL to be technical?
This is a high-speed flow.
Yeah.
So
and they're equal.
This is equal.
Yeah.
If it's high speed.
But does the terminology matter in terms of the
Terminology means what?
like? Because it's a 3D airplane, so you would use
That's right.
big CL.
That's right.
Okay.
So this is the lift coefficient for wing.
Yeah.
This is the lift coefficient for
Or
airplane.
the unit.
Yeah.
Okay.
This is a drag coefficient of a wave for wing. This is the drag coefficient of an airplane
Okay.
due to wave drag.
Okay.
This is again high speed only. Do not do the same thing for low speed.
Yeah, that's true.
High speed in this case means supersonic. This doesn't apply for low speed. Okay, let's be careful about that. Low speed, of course, those two are different. Yeah. Okay. So this is again just to estimate it. So Prandtl gravity is essentially estimated by you. Okay. This is not based on the theory. Let's be careful about that. If the airplane starts flying supersonically, drag and lift coefficient for 2D cross section and then wing is about getting the same. That's what it is. Okay. So this is the estimated value. So CD of a wave drag coefficient is 4 times alpha square root of m infinity square minus 1. If you try again, once again, 4 times 0.087266 radian. This thing square root 3 square minus 1. This is 0.01077. So now your flight is at 22,000 feet. So you can pick up standard value of 22,000 feet. Density of air 0.0011836 slugs per cubic foot. You can get this value out of your standard atmospheric table, obviously. Speed of sound. This is the square root gamma RT infinity. Of course, you're using T infinity standard 22,000 feet altitude value. This is going to be 1028.0 6 feet per second. This is the speed of sound, 22,000 feet. Now, free stream Mach number is 3. This means that what is the actual airspeed? V infinity is 3 times speed of sound, which is 5,635.21. No.
Should be like 3,070.
That's right. I was looking at different things. So 3,085.8 feet per second. So this is your actual flight airspeed. Out of this, you want to find out dynamic pressure of free stream, 1/2 rho v square. Density 0.001186. Slugs per cubic foot. Okay. Velocity is 3,085.8 feet per second distance square. Okay. So dynamic pressure is 5,635.215 pounds per feet square PSF. Insane. That's a huge value. Of course, you're flying Mach 3. Now, lift per unit span. Q infinity times C times CL, which is 5,635.215 PSF. Chord length is 10 feet. CL is 0.1234. This is going to give you lift per every unit span of your wing. 6,953.85 pounds. 6,900 pounds. Drag due to wave drag coefficient. Q infinity C, CDW, which is 5,675.215 PSF. Again, 10 foot multiplied by 0.01077, which is 606.91 pounds. So this is a drag due to wave drag shockwave formation. This is a lift per unit span. Go ahead, question?
So this is for a constant chord, right?
Yeah, because this is a per unit span.
Yeah, okay.
So this is a section problem. Yeah, go ahead.
For this plane, if you wanted to find the total lift per unit span, you would double it because you have 2 wings, right?
No, wingspan to wingspan. You need to have a
wingspan,
wingspan. Yeah. Multiply by wingspan gets you actual
Right.
total lift of your wing. But the wingspan should be very small because the supersonic.
It's supersonic, right?
Yeah.
It's like a bullet.
Yeah, but this is actually. Go ahead, question. Go ahead.
So it looks like there's a point when alpha becomes 1 that the lift coefficient and the drag coefficient are equal. Is there a term for that point, or is that significant in any way?
Drag coefficient and what lift coefficient cannot be equal to each other. This one.
If alpha was 1 in those equations, the coefficients would be equal to each other. Is that significant in any way?
Coefficient is equal to each other between 2D and 3D you're talking about?
No.
Between the coefficient lift and the coefficient of drag.
Coefficient lift and coefficient drag are completely different. It's not going to be the same. I never said that.
If the angle of attack alpha is 1, then both of those equations are equal to each other.
Just a coincidence.
Is that significant in any way?
Possibly, yeah.
That's 1 radian.
1 radian, right?
Not a degree.
No, it's not a degree. 1 radian. 1 radian is huge. And then this is already 5 degrees, right? Radian, in terms of radian, this is 0.08 radian. It's 5 degrees. This is already suicide maneuver in Mach 3. Think about that.
Oh yeah.
Yeah, of course, you're going to rip off. Look at this value, 7,000 pounds of force. What kind of airplane can you sustain? Well, this is essentially suicide. Mach 3 at the pitch up 5 degrees, you're gonna probably destroy your airplane.
What do you do? What?
Well, you cannot do that, probably.
You're at
Control
60
surface is not
degrees.
strong enough to
You
do
would
such a
get
thing. So anyway, yeah.
something
Okay.
like that. No.
So again, that's probably coincidence, but will never happen, I think. This is again just estimated variational curve fit of the data for supersonic flight. Okay. So again, we're not going to cover any more detail in this AE1. AE2, hopefully, I don't know who's teaching, but that person is going to cover more on supersonic flight.
Is it only Scott?
I don't know who's teaching. It's not my business. my job is done in the other one. Any other question? Thank you for your question. That was Caleb, wasn't it?
Yeah.
Okay. Good.
Yeah, that was me.
Okay. So let's get into now unit D1, which is the 3D wing. Okay. And then today, and then 2 more lectures, we are going to hopefully finish up this lecture. But suppose if I cannot finish up, I'm going to take the rest of the lecture, the video, and then give it to you anyways. So I'm going to well, I'm going to cover material anyway, no matter what. Okay. I mean, your response shouldn't be, oh no. Your response shouldn't be yes. Because I try to satisfy you. Your pain, lots of mess. Okay, anyways. So you're not gonna miss anything, but let's just take a look at 3D wing. Go ahead, Robert.
Can you go back to the C? I just want to see. Okay, sorry. Okay. Thank you.
So 3D wing. 3D wing, we are going to actually introduce one more design parameter, which is something called aspect ratio. So aspect ratio is the only design parameter if you design like a chocolate bar wing, right? Constant cross section, you just create the wing out of it. The only design parameter is aspect ratio. That is the wing you are going to test it in the 2-dimensional wind tunnel testing, quasi-2D. The purpose here is, of course, you create the wing with certain aspect ratio with a constant cross section. You're going to measure the lift, drag, and moment divided by this wingspan gives you lift and drag and moment per unit span, and then normalized by Q infinity times chord length, so chord length square. It's going to get you section lift coefficient, section drag coefficient, section moment coefficient. That is 2-dimensional data. I think we covered that. So that's the starting point. Okay. So starting point, basic definition of airfoil we've been talking about is this. This is airfoil. Airfoil is, if you create a chocolate bar wing, you just cut off a unit span. Okay. Out of that, you can determine section lift coefficient, section drag coefficient, section moment, typically quarter-chord moment, or could be section moment at aerodynamic center. You can determine all of those things so that actually satisfies your needs of what kind of cross-section do you want to choose to begin with. In other words, cross-section is going to be chosen first to design your wing, that is X via 5 always. Right? Okay, so that's the starting point. You're going to choose the particular airfoil, and then you can possibly use the same cross-section, I mean, same airfoil shape, not necessarily the cross-section. You can change the cross-section, alter it. That means you can introduce taper. You can change the chord length from root to tip. Okay, that's the tapered wing. You can do that. Or you can actually put in the sweep. In other words, chord length is going to be shifted linearly or non-linearly, either way. You can create wing sweep. Or you can create the dihedral by just changing the angle. So you have lots of design parameters, choices you can play with using X via 5. That is the beauty of that software, because that software is a design tool. But the design is based on the data given. Data is built up by your selection of airfoil. You have to select your airfoil to begin with. You can choose single airfoil, or you can choose multiple airfoils. But if you choose multiple airfoils, you have to run multiple airfoil simulation on 2D and then build your database. Otherwise, that software doesn't run. Okay? So those are the kind of things you probably need to find out as a team. Okay? I think the good place to find out is this one. You need these 3 notes. This actually gives you some fundamental how to get started demo or examples. Let's start with 2D and then use that 2D database to design 3D wing kind of thing. This is a good place to start. Okay. All right. So here is the wing. So you can introduce a new design parameter, which is aspect ratio. Aspect ratio is span, wingspan squared divided by wing ground form area. This is ground form, okay? This is going to determine aspect ratio. Aspect ratio is a quite important parameter. Okay, so next page. So once you create the wing, you're going to introduce a completely new idea in which you haven't even think about when you choose your 2D airfoil. Something called induced drag. This is something completely unique. You can only find out by making your 3D wing. This is going to all of a sudden show up and add it to your drag. This is a 3D wing phenomena, 3D phenomena, 3D wing. Once you design your 3D wing, now you are going to determine how much induced drag we are going to have. Okay? So let's talk about induced drag. So this is a unique for a 3-dimensional wing. Once you design your wing, what happens here is, of course, you're going to introduce your wing tips because this is no longer infinite wing. Wing needs to be terminated at the wingtip. Now, what happens here is upper surface is typically on your wing, you have a lower pressure, and the bottom surface is usually high pressure. So wingtip is a location where high and low pressure meets up. As a result, you are going to have flow tendency curling around at the tip. This is called wingtip vortices. Here we go. Have you ever seen this? Sure. I have a video. Let's take a look at video. Wingtip vortices. There's no audio, but here we go. So this is the wingtip vortices. It's going to probably keep going on and on for a few times. Okay. So wingtip vortices actually induce overall downdraft of air in motion. Is that right? Mm-hmm. So this is the wingtip vortices generated at the wingtip. At the same time, you're going to see the overall tendency of downdraft of the wing air. So this is downwash. Okay, important term. So wingtip vortices actually create the downwash. Let me just put, so this is a downwash. I'm going to use probably lowercase w. This is the velocity in the direction downwards because of the presence of wingtip vortices. This is actual thing. So this actually creates induced drag. Of course, you have to create the wing in order to find out how much induced drag you're going to have. Of course, you can minimize by doing very good design of your wing. Even though you choose a very nice cross section by doing poor job of doing wing design, your airplane ended up being massive failure or joke. I mean, there are so many airplanes in the past designed like a joke. Oh, it didn't work at all kind of airplane. I had a series of that kind of lecture, but nowadays I don't do it anymore. Okay, so next page. So what does wind downwash do? Over.
Yeah, I just wanted to make sure, is this just for, is it at a high speeds or both high and low speeds when this happens?
High speed is supersonic, right? High speed is, again, physics is going to be different.
Okay.
So,
this is very normal.
Again, high-speed flow, you almost always concentrate on what kind of shock waves formed up. And then, so that's a different flow regime, supersonic aerodynamics.
So this is just subsonic.
This is probably subsonic to transonic.
Transonic. Is transonic the?
Transonic is a high end of subsonic. So again, people call that still road speed because you didn't go across the speed of sound. Okay, so it's going to be different. But anyways, more or less, it's going to be very similar too. Magnitude will be different, obviously. But when the airplane, even in low speed subsonic or high speed subsonic, which is transonic, you're always going to have this downward. Okay. And then this magnitude is not even constant across the wingspan. It's not constant. Okay. So, but the presence, if you take a look at the cross section of a wing at a certain location, this is airfoil. Now, this airfoil experiences two things. One is, of course, this cross section believes that I'm pitching up this much angle, geometric angle of attack. This is geometrically, you are pitching up this much alpha, angle of attack. However, because of this presence of downwash induced by wingtip vortices, the direction of this B infinity itself is going to be changed effectively. Okay, so the presence of this downwash actually changes the incoming free stream direction, reducing this much alpha. So this is the geometric angle of attack alpha is going to be now reduced into effective angle of attack, which is less than alpha. You know what I'm talking about? And you're going to actually reduce your effective angle of attack. Go ahead.
It looks like that reduction in angle is the same angle as from your chord line to the bottom surface of your wing.
Not necessarily. It depends on how much W you have.
That's just an example. It's not a every case thing.
Right.
Got it.
That's right. Okay. So anyways, that's one thing. So I'm going to risk it. Number one negative effect is alpha is reduced to alpha effective. Now alpha effective is equal to alpha minus alpha induced. Alpha induced is the induced angle of attack due to downwash. In other words, this is alpha I. Okay. So you're going to lose this much alpha I from your geometric angle of attack. So in 2D airfoil, suppose you read off the NACA airfoil data. Well, I'm using standard 4-digit. 5 degrees of angle of attack. I'm expecting 0.7 CL. So I'm using that same thing to create the wing with the same 5 degrees of angle of attack. Are you going to expect the same 0.7 CL for your wing? No, it's less than that. Okay, it's less than that. So number two, this is bad enough. We're going to talk about that. Number two, even worse. Number two is this. Because of the incoming direction of a free stream is changed with alpha I, the lift is completely perpendicular to the incoming direction of B infinity. However, this is going to be tilted backwards a little bit with an angle of alpha I. So that means you are going to introduce this much originally portion of the lift now becomes the drag. Okay? So suppose if you are creating huge amount of drag, quite a significant portion of that huge amount of drag, I'm sorry. You've been creating huge amount of lift, let's say such as glider or something. You did an efficient design of glider. And then this glider was producing huge amount of lift, but okay, quite significant portion of that huge amount of lift now turns into drag as it is. It's called induced drag. Okay. Induced drag is at it. This is DI. Go ahead.
Does the induced drag generate any sort of moment since it's off? It's not parallel.
That's
to-
right. Moment is also added to.
Oh boy.
That's right. But this is huge. Portion of the rift now becomes drag. This is actually called drag due to rift. So ironic. Suppose if you have a very efficient wing creating huge amount of rift, it actually you also create huge amount of induced drag.
Is that like how flaps work as well?
Flaps is going to temporarily increase your rift, but at the same time, it's going to increase the induced drag big time. So, yes, that's correct. Right.
This is only caused by wingtip vortices.
That's right. This is caused because now 3D effects comes into play. Wingtip create this, and then downwash, and then it all causes this. Those two things happens. Okay. You can only predict those two by designing 3D wing. That's why the software is quite important, because your software actually predicts those two. Those are very important design parameters you need to find out. Okay. No one can tell your wing is good design or bad design by looking at this. You have to look at this. And also, today's jet airliners always comes with very weird, unique design of a wingtip that is going to have a major impact on formation of wingtip vortices. Okay, so again, by assuming small angle alpha I, this is induced drag. Okay, go ahead.
Is it to drag due to lift because it's like the lift causes?
Yes.
Lift causes drag.
Because portion of the rift becomes drag, that's why the name drag due to rift.
Oh, okay.
Yep. Okay, let's move on next page. So we have to take a look at, this is the wing frontal view. So when you create or design your wing, you are going to also at the same time compute which section of your span of your wing produces how much lift to support the wing, okay? So this is span-wise lift distribution. X prime 5 actually can compute this all the time, okay? Quite important, span-wise lift distribution. This is very, very important design parameter. Now, span-wise lift distribution, ideally speaking, if you have elliptical function, okay, this is ideal. Ideal means elliptical function lift distribution. Very nice, smooth distribution of the lift, okay, from the center of the fuselage and then tip of the wing. Very nice span-wise lift distribution. That's going to be an ideal situation. Ideal means efficiency maximum, max efficiency. Max efficiency means that uniform downwash. Downwash now becomes uniform across the span. Uniform downwash. Sorry. Okay. This is ideal. No one can make ideal wing. It's impossible. One of the reasons here is, obviously, you're going to have a fuselage. Fuselage is usually not going to contribute to generate the rift. So oftentimes, typically, you have a dip of a rift distribution in the location fuselage. Okay. And then you can never have a perfect elliptical function lift distribution. This is only theoretical. However, if you follow through the theory, you can determine ideal, which is uniform downwash. Suppose if the uniform downwash, this is the equation of induced drag coefficient. Induced drag coefficient. Only if it is ideal. Okay. So induced drag coefficient for ideal case, which if you have a wing with a complete elliptical lift distribution across the span, CDI, this is the induced drag coefficient. This is, by the way, drag coefficient induced divided by Q infinity S. This is CDI, okay? So lift coefficient square divided by pi times aspect ratio. Obviously, if the CL is big, this is big. Very ironic. If you create a large lift surface, it is going to also create a large induced drag. And then aspect ratio, higher aspect ratio is better, it looks like. What is the higher aspect ratio?
That's thin wings that are lighter.
Oh, it's like a this kind of wing. Right. Oh my goodness. Have you ever seen this?
Gliders.
Gliders, yes. So gliders essentially purposely designed to minimize the induced drag so that maximize the gliding distance or endurance, I should say.
We just can't go very fast.
Or danger endurance, I don't know. I have to take a look at flight mech. Flight mech, you have equations for those, of course. Okay. Anyways, so if you design high-speed airplane with this kind of wing, have you ever seen that?
Oh yeah, we have one more.
Oh yeah, so yeah, this wing, great, but what about CDI? It's terrible. Okay, so it's always trade-off. Good high-speed airplane is a terrible low-speed airplane. Terrible low-speed airplane is a good high-speed airplane. One of the nightmare is induced drag. How do you handle that kind of thing? Okay. So next page. So let's just recap. So what is the total drag you create for the wing? Go ahead, question.
For the bigger wing, is that like more drag maximum?
Sorry?
With the bigger wing, is that maximum?
Bigger wing. Let's not use that kind of word.
Like
This is a high aspect ratio.
high aspect ratio.
Yeah. This is low aspect ratio. Yeah. So obviously, low aspect ratio comes with higher induced drag coefficient. Okay. Looks like we got about 5 more minutes. So next class, okay, next class is Monday. So we are going to take a look at the total drag. Total drag is something called drag polar for 3D wing. We are going to construct the total drag based on the combined two things. One is a profile drag. When you choose your cross section of your airfoil, you are going to determine profile drag. Now, as you design your 3D wing, you are going to come up with the induced drag coefficient. You have to add them together to have a total drag coefficient. Now, important thing is this is lowercase, this is uppercase. Can you add them up? This is a 2-dimensional parameter. This is a 3-dimensional parameter. How on earth you can add up those two? Anybody? Go ahead.
Multiply your 2-dimensional parameter by your span to get the.
Actually, those are coefficients. So dimensionless. That's the beauty of you can add them up. Dimensionless. That's the beauty of aerodynamics. So we can add them up to create a total drag coefficient. So we talk always coefficients. Okay, so that's quite important. So we can add up 2D airfoil and 3D effects coefficients together to come up with total drag coefficients of our entire wing. Okay, and then we're gonna plot the drag polar. So next class we are going to take a look at that, and then we are going to predict the wing total drag based on the addition of a 2D profile plus, okay, induced drag. Stephen is probably doing something like this, yeah? Using.
They're not this morning, actually.
Yeah, that's right. You've been doing that in this morning. So, anyways, so next week, Monday, we're gonna continue on discussing about this, and Wednesday, probably half of the class, the special project team of X55 is gonna share what they're doing. Right. Okay, so let's stop here today.
Wait, half the class, so that's like 25 minutes. And
Well, you
there's
don't have
two
to
of-
go that long.
Well, there's 2 of us, so that's like roughly 12 and a half minutes each. I
Well,
don't know if I'd be able to cover all mine in 12 and a half minutes.
if it's shorter, that's fine.
No, it's too long. I haven't even finished and my presentation's over 35 slides.
No problem.
No, I have to. Aspect ratio.
Oh, no.
That's grandpa.